If you can sit through this entire episode, hats off to you, sir or madame, because this is quite the rant. Hopefully, at least you guys get something out of it. I'm your host, Brody Frye. This is the Mind Hiking Podcast. Hopefully, you enjoy and stay tuned. Hello and welcome, everyone. I'm your host, Brody Frye, and here we dive deep into difficult questions. We'll map out thoughts, theories, and crazy ideas for the love of knowledge and growth. So, how do we answer some of the mind's toughest questions? This is the Mind Hiking Podcast. All right, guys, let's try to tackle this one. I got my chocolate milk here, so go ahead and grab yourself a drink or kick back and relax. If you're driving, just relax, but pay attention. So, also, just a little disclaimer, I never went to college, and everything that I know is self-taught because I didn't care about school. I got out of there as fast as I possibly could. Graduated a semester early and left after fourth period every day for junior and senior year because of work program. So got out of there. School wasn't for me. I found a passion for learning and knowledge after the structure of academia, because that just the educational system is not for me. So anyways, gravity. Let's get to the gravity of the situation. So if you look up gravity and what it is, the definition of it is that gravity is a force by which a planet or other body draws objects towards its center. The force of gravity keeps all of the planets in orbit around the sun. That's interesting to me. I don't know. I've always been fascinated with this subject. So back in I think the original, not discovery, because they never discovered it, but the original introduced theory date was back in 1930s, I think. But it was popular up until the 80s and 80s and 90s, actually, that there was these particles called gravitons, and those were what scientists believed were the cause of gravity. And there was just particles that just, they believed that these particles were what gravity was, that it was a particle and that was the force that was pulling you towards large mass objects such as Earth. And now there are people that still believe that, but again, it's a graviton particle has never been discovered because they don't exist. But there are people that still believe that. What more scientists are starting to turn to now is that gravity is a wave, and that's kind of new science. A lot of people don't really want to accept that, but people believe that gravity is actually a wave. Now, again, I never went to college or anything, and I'm just going to give you my nerdy thoughts and opinions. I grew up as a farmer, and I just have a regular job, and I just think a lot. So, that's closer. I think that makes more sense, that it's a wave, because I do believe that it can be, warped. I think it can be affected. And I actually thought of a hypothetical warp drive, and then I started looking it up, and it's already actually been theorized. And what I found it to be called is the Alcubierre drive. And it was first proposed by Miguel, I believe is his name, Miguel Alcubierre. And it was just a warp drive idea for a hypothetical. Obviously, we've never had the technology to be able to do something like this. This is all just theoretical, but basically a hypothetical spacecraft that could achieve like a faster than light travel. And the idea was that it's a technology that can contract space in front of this hypothetical ship and then expand space behind it. So basically you're warping it. That's why they call it a warp drive, is because it's warping space-time. So it's just like contracting in front of you and then expanding it in front of you. But there's problems with it, with the idea. It's not. Most science is based off of the equations that, or at least like theoretical physics is based off of a lot of Einstein's work with special relativity and the relation of speed and mass. And so one of the issues with this is essentially what people say is the Alcubierre drive is implying that there will be a pocket of like lower density than a vacuum, like the vacuum of space. Because it's basically like a Venturi. So like, or like in simple terms, because again, if you can't explain things to a 6-year-old, then you don't know it yourself. But essentially what I'm trying to say is like take your garden hose and put your thumb over it. All of a sudden you're creating high pressure in the hose because you can feel the force on your thumb if you put your thumb over the end, and then it's like super high. So like that high pressure creates high velocity past the Venturi. So you're creating a pinch point essentially. So then the high velocity is the water comes shooting out faster, shoots out of the hose faster because of this Venturi. So you're creating a high pressure point, like a high pressure focal point Venturi, and then a high velocity with low density. So when you have that low density, that's high velocity because everything's expanding now. So that's essentially what the theory would be with this Alcubierre drive is same thing. Basically it's like I just thought of this now, but it's basically a Venturi spaceship. So and then the ship just acts as the Venturi, the pinch point, and it's just spitting out high velocity in the back, high velocity, low density space time. And that's the possible issue. But my thought behind that is the whole theory of it is it's warping space-time. It's not taking it in like we know matter and then spitting it out the back like that. It's warping. So like somebody's like standing on the sidelines just like watching this ship pass. Obviously you can't watch something that fast, but like nothing would change for that person watching this thing go by. Like it's not like they would go nothing else changes. The perspective of the person standing watching this ship go by, nothing changes. It's the ship itself is warping space-time so that way it can travel through it. And most likely that ship would probably be invisible to the bystander anyways, because it's warping the space-time to the point, and in the perspective of the bystander, nothing's different because the bystander is going to be still in this fabric of space-time and not in that bubble of the hypothetical spacecraft. So just stupid stuff that I think about all the time. But anyways, so I was thinking about it again the other day, and about gravity and like what it could possibly be, because I'm like I think about the motion of the planets and the orbit of the planets around the sun and things like that, and then like comets and asteroids and just the beautiful dances they perform around us, and just like it's just fascinating to me. But why is there gravity? Why are they like the dances are gorgeous and beautiful, and you can understand why they're moving the way they're moving the way they're moving, because they're falling into each other, but since it's a sphere, it's falling around, and it's a constant, these stars and planets are falling around each other. It's just like a constant motion. It's at the problem is it's hard for people to wrap their mind around this, because so much time has gone by for these things to stabilize. Like these things, it's like a gyro, where like if you start up a gyro, it gets so wobbly and unstable, and then it finally like catches itself and stabilizes, and there it is, like just spinning perfectly straight up on the table. Or like growing up, have you guys ever had like a spinning top, and you like spin it with your fingers really quick on the table, and it rattles around and then like stabilizes itself? That's how these planets and stars have created this dance with each other. It's just over so many billions of years where they stabilize themselves. So much chaos happened after the theory of the Big Bang theory, and that's how like so much chaos breaking apart things, just it was an explosion, and after billions of years things stabilized, and here we are today, where now we got these beautiful dances, and occasionally you'll still have impacts and things like that, but it's getting more and more stable as time is going by, and that's where we get this. But why is that? Like the dances around each other is totally understandable, because they are just falling around each other. So now you got these planets, like the moon is falling around the earth beautifully, as the earth is falling around the sun beautifully, as the sun is falling around the next biggest star, and we're all falling around the black hole in the center of the Milky Way galaxy, and the Milky Way galaxy is falling around who knows what, as it's about to make a slower collision, because the bigger the object, the slower these things, the more time it takes. So as we're about to collide with the Andromeda galaxy, but anyways, which is our neighboring nearest galaxy, but things are just falling around each other. And why do they do that? Why do they fall around each other? It's always been so interesting to me, because it's like I'm going in circles here, but it makes sense why that happens. But like, how does that? I don't know. It's my theory. My idea was the fact that they say, and it's tossed around so much, that gravity is a force, the force of gravity. It's a force. And I'm thinking like, maybe they're wrong about that. Maybe gravity's not a force. Maybe gravity's not pulling you, and there's also, I've talked about this in other episodes, where it's actually more of a push than anything. And it's not like the earth, because like, how could gravity be pushing us down to earth? That doesn't make any sense. But it does it's not like the earth is expanding so fast that it's keeping you at its surface. No, it's not that. It's just the progression of time is what's keeping us on the planet. So that was my original theory, is it's like the progression of time is is how gravity works, which that's still absolutely true, because If there was no time, there was no progression, then we would just be a snapshot, and that's that. So you need you have to have time to have space, because otherwise it's just a snapshot, for lack of a better term. It's like there's no action or reaction. There's no action at all. And so you need time, the progression of time, for things to happen, to show effect. And so that's where I was thinking the expansion of time is the progression of forward pushing of time, is because we're stuck going forward in time. That's it. Like, we can't go back in time. We can't pause time. We can't go faster. So, and I'll come back to time actually, but that was my original thought. But then I was thinking, and I know mass has a large portion to do with it, because the density of objects, like denser planets, have heavy, like a stronger pull, a stronger gravitational pull, and there it is again, like the gravitational pull. So like why is that? Why do we call it that? So I know density has a lot to do with that strength, but where I got to thinking about this is maybe it's not pulling, maybe it's not a force, maybe what it is like so everybody's seen like this whole example of like you spread a bed sheet out, pull it tight, and then you put like a bowling ball in the center, and then you roll some golf balls, tennis balls, and marbles or whatever around it, and you get to have this two-dimensional visual of like how space-time works, and you get to see how the planets orbit each other. And it's not a perfect example. It's just like a quick example, and some people might think like, whoa, why don't they continue to orbit around each other then? Like, why do they always roll straight to the center ball that's sitting still if that's how it works? But it's like, it's not a perfect example, because now you have an extra force acting on it. You have the actual physical force of gravity acting on your two-dimensional example. So it's not going to be perfect because there's too many variables. So it's just a stupid little visual, so that way people can try to comprehend this a little bit easier. And it is a good example, but it's not perfect. It's just a good example for what we can work with now. There's better like CGI examples that you can look online, where it's actually like a three-dimensional grid system rather than like a two-dimensional sheet. Like a three-dimensional grid system, and you can visualize the lines of the grid warping around the planet as it moves around. So you can look up videos on that, and that's a lot more accurate, but it's still not perfect. But picture that. I would highly recommend actually looking that up to fully understand what I'm about to say. But like that. So obviously mass has a major part in the bending of space-time. And now we kind of get back to gravity being a wave, like the more new science explanation. Like it's more accurate, because that does show the possibility that it can, like, space-time can flex the way it does. I feel like space-time, like, that's enough proof. I think that's all gravity is the flexing of space-time. That was my thought, where, like, and you can think about this as, like, this is going to be such a stupid example, and I never played it a lot, but if you guys have ever played Angry Birds, and there's, like, the in the space levels where, like, you shoot the bird, and it's, like, flying straight across the screen, and then as soon as you get towards the planet's gravity, like, it shows, like, it's a stupid game, but, like, it's got, like, the bubble around, and, like, as soon as your bird flies right towards that bubble, it curves, it follows that gravity, and some of the planets have stronger than other, so, like, it's actually a good visual. So if you know what I'm talking about, that's a good visual, because, like, send something like that out into the vacuum of space where gravity doesn't affect it, and then all of a sudden you get close to a large mass object, such as, like, such as like the moon and the Earth. And all of a sudden the moon gets caught in the Earth's gravity, and maybe gravity isn't pulling. Maybe it's not a force pulling the moon towards it. Maybe what it is just the curvature. Earth's mass is creating a curve in space-time, and now you got the moon just rolling around this bowl that the Earth is creating. So it's not that the moon is like being pulled towards. It's not like a force. It's just the Earth's mass creates a curvature in space-time that causes the moon to roll around us like that. Like maybe it's not like, it's not a force. It's just the flexing of, like the Earth. It's all relative. It's like the moon is just rolling on a flat surface, and it's just going to keep rolling straight. But like to the moon, it's still rolling straight, but it looks like, relatively, it looks like it's curving around the Earth because of the curvature of space-time. So it's still rolling like, and I'm just using another, like, you know what I mean? It's another stupid example because it's not perfect. I'm using like a two-dimensional mental example for a three-dimensional object. But that's what I'm trying to say is like, it's like following this density curve of space-time rather than having a force acting on it. It's not that it's acting on it, it's the flexing of space-time, which, there you go. If that's a possibility, and if that's actually an accurate description, then this Alcubierre drive is absolutely possible, because that's all the proof you need to know that you can bend space-time, because every planet and star does that already. And we just got to figure out how it's doing that, whether that's mass. It's obviously not mass, because there's like low mass, high density objects that have high forces of gravity. So then what is it then? Is it density? Is it objects that are like super dense that create like more of a flex? Because then if that's the case, then maybe this bedsheet example is a closer to accurate example than we think. Because think about that. Like, say you got like a balloon takes up a lot of space. Like that's more of a massive object than, say, like a lead ball bearing, like a heavy ball bearing. And now if you set a balloon on a tightly pulled bed sheet, that's not going to make an indent barely at all. But if you put a ball bearing in the center, that's going to dip it down a lot. So that's a perfect example. Or, I mean, that's an extreme example because I'm trying to get the visual for you guys. But like, you could even say the same thing about like a volleyball. That's not a heavy ball, but then you do a ball bearing. We're going to keep that example where that's way smaller, but a volleyball is way more massive, but it doesn't have that force. It's not flexing that bed sheet. So maybe that is the case. Maybe it's like everything's being pulled inward towards that ball bearing, even though it's a little object. So does it have something to do with density? Maybe. But also, now we can get into like light speed. They call that the speed limit of the universe. Where, you know, like you got galaxies that are hundreds of thousands of light years away, and they say we'll never be able to reach them, and blah blah blah. But with a warp drive like that, you wouldn't have to worry about speed or time, because you're warping space-time anyway, so you can go anywhere at any speed you want, and even almost damn near instantaneously. And since you're already in that bubble of warped space-time, you don't have to worry about splatting on the windshield when you try to stop super fast. So it's all relative. So coming out of that warp drive, you're reintroducing yourself into a stationary space-time fabric. So it's not like you're in the material world and you fly super fast and get shoved into the seat and then you just splat on the windshield. That wouldn't be the case with this drive. Anyways, if you're trying to go at the speed of light, it's and I have another episode on this. A lot of these things that I talk about, I have old episodes on, so I encourage you to go back and check them out. But if you're trying to go at the speed of light, it's not that that's impossible, especially in the vacuum of space. The first most obvious problem is going to be, probably the most obvious problem is that the fact that how much time it's going to take to get there, because you can't speed up to the speed of light instantaneously. You can't speed up to if you went from 0 to light speed instantaneously, you'd be just like missed on the back of the ship, because you can, and also any materials that we can come up with or manufacture to create a ship, it would never hold up to that kind of acceleration. You don't feel speed, you feel acceleration. So again, I have an episode on this. I don't want to get into it too much. You like if you're going 65 miles an hour down the highway, 70 miles an hour down the highway, and you're at that cruising speed, you don't feel it. But if you jump out and into a sign or something like that, you feel that sudden stop because that rapid deceleration. And then same thing goes for acceleration, where if you're sitting stationary and somebody like punches it and you start accelerating, you get like thrust back in your chair. It's the acceleration and deceleration that you feel. But the speed, again, it's all relative. The speed you don't feel. You could be traveling 1,000 miles an hour, 100,000, 1,000,000 miles an hour. As long as your biological body can withstand that acceleration, then you can reach any speed. So, and again, it's all relative. You could be going light speed compared to something that's like, if you're going half light speed and then another object is coming past you at half of light speed, you're going light speed relative to that object. So again, and it's the same thing with like, if this is another stupid side example, but like if there's an animal in the road and you're driving your car at 60 miles an hour, you'd be so much, I know it sucks for the animal, but you'd be way better off hitting the animal at 60 miles an hour than to turn into oncoming traffic and hit somebody else coming at you at 60 miles an hour. Because now instead of hitting an animal at 60 miles an hour, you're hitting another solid object the same size as you at 120 miles an hour. And also the animal's going to have a lot more give. And even so, you'd be better off like just pulling the wheel into the ditch too. So that's just another side tangent, but that's what I'm trying to get at is the addition of the relative speed of the objects you're looking at. But anyways, so say you're going at the speed of light, or say you're traveling away from Earth and you're going, okay, well, actually, I'm going to backtrack and tell you the other obvious problem I was going to originally say before I got majorly sidetracked. But the other major problem would be just space particles. If you're traveling at the speed of light, a speck of dust is going to rip your ship in half. So you can't hit anything if you're going that fast. So it's like, yeah. So anyways, that's an obvious problem. So say that hypothetical spacecraft has like a force field around it, which again, in theory, this Alcubierre drive warping space-time, that shouldn't be a problem hypothetically. I don't believe. Again, this is all uneducated nonsense coming out of my mouth right now. This is just my my thoughts running wild, and I just have a super hyperactive mind and brain, and I just like to keep it busy with this stuff. So in my mind, this theory, you shouldn't have that problem when you're warping space-time because you're in that bubble. But say you got like a force field bubble around you, and you're going in the material plane. Like we're talking now in the material plane. Like say, like within the fabric of space-time, you are going at the speed of light, and you have a force field around you, so no objects can suddenly stop you. So you leave the planet Earth, you're accelerating towards light speed out into space, and what's going to happen is you're looking out the front windshield, and all the lights and all the stars, even the ones next to you, are going to want to like curve in, and they're going to look like they're pushing farther. And it's like, okay, so think about this. Think of a fisheye lens. Like everybody's seen like a fisheye lens on their phone or whatever. Like you can think of a fisheye lens. Like that's what it's going to slowly do that, where it's like if you put a fisheye camera lens on your phone, all of a sudden everything looks so much smaller, but you can capture such a larger picture, right? That's the curve, like the curved glass. That's what you would see if you're traveling even near the speed of light. If you're traveling like 60% or more of the speed of light, you'd start to notice this, where you get that curve. And what's going to happen behind you is it's going to expand and get closer. It's going to like wrap around because, and I know that doesn't make any sense. It looks like everything's getting further away from you the faster you go. But think about it this way. Think about like the rain, when you're driving in the rain, like say it's like not a windy day and it's like rain's falling down, you're driving, it's like the middle of the night, you got the headlights on, you can see the raindrops really well. Say you're stopped at a light or something. Raindrops are falling straight down. You can see them falling straight down. And then actually a better example might be when it's snowing. Sorry for people that don't live in wintry climates, but you have a better image of this while in the snow because it falls a little bit slower, so you can picture it better. But like either or, rain or snow, you'll get the idea. But like you see it falling straight down, but then as you start moving, it looks like it's the drops or the flakes are starting to fall at you, right? They're like coming at the windshield. They start to angle. And if you look out the side window, it looks like they're starting to fall at a 45. So, and the faster you go, like if you're on the highway and it's snowing or raining, it literally looks like they're shooting straight at you because you're going so fast. You're going that much faster than what they're falling. Like the speed that they're falling versus the speed that you're going at them. So that's essentially what's happening. Like the photons of the light are coming, you're going into them so fast that it looks like it's coming at you rather than coming at you from the side or anything like that. Like it's going to curve, it's going to fisheye lens outwards. So that's how that works. And then everything behind you is going to look like it's coming closer. You look out the back window and all of a sudden it looks closer but expanded because all that light's wrapping around to the front, the direction that you're going. So it's going to be like you put on like a zoom lens, like a really close up zoom lens on the back, and everything's like fisheye lensed out the front. So basically everything, like everything's like squishing. It's like squishing down. And now where I said you get into time here is you're going to start warping relative time. For you, nothing's going to change. It's again, relative, everything's fine. You're not going to feel any effects or anything like that. Especially standing on the ship where you can stand there totally fine as long as you accelerate it at a comfortable speed. You're not going to feel any effects or anything. You're just going to have these like optical illusions from the insane speeds that you're reaching. and they will be optical illusions up to a point, but you'll start to have physical effects when, again, physical effects relative to where you came from. Now that's where it gets super tricky, because now what you're doing is changing the trajectory of time for you versus the trajectory of time. Sorry, I forgot to silence the dogs. Normally I put them on like silencer mode by taking their collars off, but I forgot to take their collars off. So sorry about that. But that's Bailey right there. She's a miniature Australian Shepherd, and then I got Baron, my big boy. He's a chocolate lab. But anyways, so you have where was I at? Sorry, I lost my train of thought. You have you're leaving the planet Earth at this insane speed, and you're changing what you're doing is you're changing your time trajectory. So now, as you go faster and faster, the Earth's clock is going to tick even faster, and your clock is going to tick slower from and again, it's all relative. So like if you're on Earth and there was a big enough clock and you could see it there, literally physically, the ship's clock is going to actually tick slower as it's going away. And you know this because, again, trying to explain it to a 6-year-old so you guys understand that I actually understand what I'm talking about. You know this because of the speed of light, and as you approach the speed of light relative to Earth, the photons, which is how we see light, basically a bunch of millions of photons are shooting into your eyes right now if your eyes are open. The photons are struggling to get to the ship because if you're going close to the speed of light, the photons behind you are struggling to catch you. So now you're looking at that ship, and because it's going so fast and those photons can't catch up, it appears like that like it's going, like the clock is going to be moving slower for that. So you're on Earth, you're going to be like being able to like doing whatever relative to the object traveling almost at the speed of light away from you. And again, like the distance is obviously, this is all super hypothetical. And then same with the ship. If you're on the ship and you're traveling almost at the speed of light looking back, first of all, everything's going to start to get really dark because you're going to lose the amount of photons that you're taking in because you're going almost the same speed as them. So they're struggling to catch up to you. But because of that, everything's going to be going at rapid speed because you're not able to take all that in. You're not able to see it. So everything's traveling so much faster because you're shifting that time axis. So you're like that time baseline. So now when, like, if you travel at the speed of light away for however long, and then you decide to come back, you're time traveling. That's literally time travel because if you traveled out for so long and then you come back, like you could have had like 1,000 years pass by on Earth and it didn't even feel like a thing for you. Like it could have been 5 minutes for you. And that's the same case with where I was saying about light speed travel and traveling to, people say that you can't reach like stars or galaxies that are like hundreds of thousands of light years away, like at the beginning of this episode. That's not the case. You can. But and the reason why people say like it's going to take literally 100,000 light years for you to to get there, if you're traveling at the speed of light, that's going to take 100,000 light years, or that's going to take 100,000 years at the speed of light to get there. And that's not the case for you. That's the case for them. That's the case for people that are being left behind because of special relativity, Einstein's theory of special relativity, because it's all relative. So if you're on the spaceship, it'll actually, like if you travel at the speed of light out to something that's 100,000 light years away, it could take minutes for you. You'll reach it because everything's like warping. Like I said, with the image of light, everything's warping in front of you. And there's a phenomenon that I haven't explained yet, but again, I'm throwing so much at you, but essentially what's going to be happening is something that's called length contraction. And that's again, like the bystander perspective of what's happening in your spacecraft, or to your spacecraft, where from the perspective of the spacecraft, everything's like fish-eyeing in front of you and then like squishing up close to you in the back. So then from the bystander perspective, if you could see that ship, it's actually contracting, length contraction. Like it's literally like squishing in on itself, like shortening itself. And now project that across your journey. That's a real thing. If you're traveling near the speed of light and climbing up to it, you're shortening the distance of your journey. So you actually don't have to travel the amount of distance that it actually is, the faster towards the speed of light that you go due to length contraction. And that's real. But by the time you get there, yeah, it's been 100,000 years from the perspective of Earth, and everybody you know would have died, and like all of your ancestors down to the point where they'd forgotten about you is all that's left. And they would have so much more technology and blah, 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 blah. But it's special relativity. But for you were able to get there in what seemed like minutes. And that's how that works, traveling at the speed of light. That's time travel, speed of light, and length contraction. Okay, I know this is kind of a cliffhanger ending, but I have to go to the bathroom so bad. I slammed that chocolate milk, and I gotta go. So I'm sorry. I hope you guys enjoyed this episode. If you like what I'm doing here, please give the podcast a 5-star review on Spotify. It really helps. Follow the podcast. That really helps also. Turn on those notifications so that way you guys don't miss an episode. And the best way to help this podcast grow is to tell somebody about it. If you have a favorite episode, send it to somebody and share, spread the word. It's awesome. I always appreciate your love and support. And also follow me on Instagram, Brody_Frye_63. And you can keep up to date on some of my personal life stuff. And also I post about the podcast. And then also my TikTok is just the Mind Hiking Podcast. And I actually post clips of episodes, some old episodes, sometimes upcoming episodes. So you guys get sneak peeks. So check all that out. And I really appreciate your support. Thanks for tuning in, and have a great rest of your Wednesday if you're tuning in on release day. I appreciate it. And see you guys next week. Peace out.